Wi-Fi. I'll start recording. This is it's quite a lot. I'll try. This is sort of a combination of a couple of talks actually, which I've tried to put together. So, but I mean, hopefully, that this is just general advice on what to do if your program doesn't go as fast as you think it should go. And we start off with some general observations about parallelization and such like, and then go on to a few more detailed things about how, which link more to the previous lecture about how sender and receiver are actually implemented under the hood. I've lost my cursor. So you can divide the overheads up into sort of four main categories in your parallel program. Why doesn't my program scale linearly, for example, or as well as I should? One is lack of parallelism, one is load imbalance, one is synchronization, one is communication. The first two are very much due to your algorithm, and it's very hard to do anything about them. Okay, so Ian said I just tried the single notebook with 128 tasks. So what that will actually do is that will actually that is still doing a ping pong between two processes, but they will be physically on different places on the node. So when we by default, if you just run two MPI tasks, they are on the first two CPU cores, so they're very close together physically. They're on the same physical processor, sharing the same L3 cache and stuff in the same NUMA region. If you're on 128, it ping pongs between ranks 0 and 127, which are at the extreme end, so they're on different NUMA regions, different processors. So they're very different. But that's interesting. That, again, I don't understand that. So there is definitely some, you are seeing effects of the way that the memory is laid out and the way that copying happens on a shared memory NUMA system, but I can't quantify why it's yeah, caching makes up. Yeah, I still don't understand. I can come up with lots of reasons why it's slow at large sizes, because you can say you're blowing the cache, but it's not clear why there's such a difference between synchronous and asynchronous, synchronous and standard. You can come up with lots of reasons why for large messages it will be slow because you don't have cache, but not why there's a difference between the two modes. So that's interesting. The first two, lack of parallelism and lack of load imbalance, are really only can be addressed by improving your algorithm, which is kind of outside the scope of the course. The synchronization and communication you can try and affect by the way you write your MPI. So, you know, lack of parallelism, task maybe, this is Amdahl's law, task may be added because only a subset of tasks are computing, there's a serial component, and the typical thing is work done on task 0 only. For example, naive IO, for example, or setup. So really the only cue is to read down the algorithm. That is really all there is. Or if we're not going to cover it in this course, but if your overhead is IO and you're doing IO through a single controller process, then the solution would be to use parallel IO, such as MPI IO, but we're not going to cover that today. Load imbalance is much harder. All tasks have some work to do, but some have more than others. It's a much harder problem to solve. If you're doing OpenMP programming, shared variables, threaded programming, then it's really quite easy because at any one point, any thread can operate on any data. So you can tell, however, with distributed memory message passing, if you want to move work, you have to move the data because you can't share memory. And in fact, it can often take such an overhead to moving work to a free processor and getting the results back is not worth doing it. There can be very significant algorithmic changes. Scaling to large process counts can be hard because often load balancing algorithms themselves don't scale very well. They take so I mean, load imbalance is a whole different topic and it's very, very difficult to solve, but it is an algorithmic question. You know, how would you notice that? Well, often if you run an MPI profiling tool, it will spend, somebody mentioned this earlier on, it'll report the amount of time spent in different routines. And often people say things like, oh, my program spends a huge amount of time in MPI or reduce. MPI or reduce must be slow, but often that's not the case. It's actually you have a load imbalance. So all of your processes are calling MPI or reduce, which can only complete once all processes have entered. There might be one slow process who's got too much work, and they come in really late. So load imbalance can often show up as a lot of time spent in receiving or calling collective routines. And so, tracing tools can often show this load imbalance very clearly. You can see that some processes are idle and so on, but these can be quite difficult to, quite difficult tools to run. But often load imbalance will show up as a large amount of time spent in receives, waits, or collectives. And that is not that the receive, the wait, or the collective took a long time. It's that a lot of processes were waiting around for other ones to arrive. So synchronization, when you send a message, or do a collective, there's both the overhead of transmitting the data, there's also the overhead of processes synchronizing with each other. And in MPI, synchronization is very much coupled to communication. If you have a blocking send or a particular blocking receive, there's a synchronization between send and receive when the data comes in. So the things where you end up waiting are blocking sends and receives, waiting for the non-blocking sends and receives, which is a kind of equivalent thing, and also collective communication, so mostly synchronizing. Okay. Now, I'll come back to some more. The use of blocking point-to-point comms can result in unnecessary synchronization. So what this can mean is if you have lots of halo swaps to do, we're going to do it explicitly in a 3D example. You've got to send up, send down, send left, send right, send forwards and backwards. What I mean by unnecessary synchronization is doing them in order, saying I will communicate with my top neighbor first, then my bottom neighbor, then my left neighbor, then my right neighbor, then my forward neighbor, then my backward neighbor. You're doing things, you're synchronizing with each communication, with every pairwise swap, you're doing synchronization in a prescribed order. The reason why that can slow your program down is that you may think that your program is load balanced in principle, and in practice it won't be. And the reason is that modern computers are very complicated, and although you think your processes are all running at the same speed, they're probably not. There's a whole bunch of things going on, but a classic one is operating system interrupts. The operating system has to do stuff every now and again. Okay, it has to do I/O, it has to do things. The operating system has to run somewhere. Okay, it has to run on one of your processes, and so different processes, different nodes don't all run at the same speed. And so, although you may think your algorithm is perfectly load balanced, it may not be. Things will run at different speeds. And so it's very important not to impose unnecessary synchronization, because that will amplify this load imbalance, even if you think your algorithm is perfectly load balanced. This, I won't go, but this was really first noticed, when was this? I don't have a date on this, it's pretty crummy. About 20 years ago, there was a machine called ARCHER2, which is one of the first machines to be built with large shared memory processors, and people noticed there that that they were suffering from load imbalance, even though they thought their algorithms were load balanced. And for example, one of the effects they saw is that they had an application, although Sage spends half its time in all reduce. So people were a lot more naive 20, 25 years ago. They ran this application, it spent all its time in all reduce. They made all reduce faster, and it made no difference. And the point was that the fact it was spending all its time in all reduce was actually due to random noise. So it was due to synchronization, and the fact that the processes weren't synchronized was due to random operating system noise, things happening. And they plotted a histogram, and you got a very, very nice Poisson distribution of how long it took per iteration of their algorithm. And it turned out here that the nodes were were checking for I/O too often, aggressively checking the disks and flushing to disk and doing different things. But this was the first time that people had built very large parallel computers out of shared memory nodes, and that people hadn't experienced these effects before. So the trick is you have to realize that your algorithm is probably somewhat load imbalanced, even though you think that it might be perfectly load balanced, and therefore to do as little synchronization as possible. One thing you can do is a very naive thing is, the collectives, if your collective takes a long time, you could just call it less frequently. And so, for example, a standard thing is to do, is you have some optimization algorithm and you are computing some error or tolerance. So you loop over lots of iterations, you update your arrays, you compute some local variable, I'll call it delta, you then do an all reducer with the global delta, and then you stop its less than tolerance. Okay, so that will stop as soon as the tolerance falls below some value. Sometimes it's possible just to say, well, actually, checking whether I need to stop, checking for the termination condition, if that's very expensive, then just do it every 10 iterations or so. Okay, just don't do it every iteration. Now you will do some redundant loops. You will maybe do 10 up to 9 redundant iterations, but that might be outweighed by the fact you're doing an order of magnitude fewer global sums. That is a nice thing if you can do it. The other thing where you might be doing this, you might just not even be using this value you might just be printing this to the screen. Okay, you might be computing some global variable leverage. Just basically just do the diagnostic less frequently. Okay, so this is only possible if this update to the arrays here, your actual algorithm is independent of this loop, of this value. Okay, if you're doing something like conjugate gradient or something, one of these standard Krylov subspace methods, then this you have to do vector dot product where the output of that dot product actually feeds into the updating the arrays. So this is only possible in certain cases. I would say the clear case is, often just printing diagnostic values to the screen, if they require global reductions, you should just minimize that. Even if so if you can just do the collect, although this feels a bit dirty, doing only checking for convergence every 10 iterations, it can actually help in practice. Barriers are almost never required for program correctness. It's a bit of a subtle point, but you have to write very, very, very contrived programs it has to be a very contrived MPI program where you require a barrier for correctness. Now, often MPI programs will run correctly with a barrier and incorrectly without a barrier. That's because the MPI program has a bug. For example, you're not waiting on a non-blocking communication correctly, and putting a barrier just happens to fix that. But so it is very, very, very rare for a correct MPI program to require barriers for correctness. So the first optimization I always do if I ever see someone's program is take up all the barriers. You see people say, MPI barrier, MPI all reduce. They'll be make sure all the data is ready, MPI barrier, add the numbers up, MPI all reduce. No. The collectives do the appropriate synchronization. Okay, you don't have to synchronize yourself. So barriers are almost never required for MPI program correctness, other than in very contrived situations. And that's just really a comment there. But really, we're going to look at communication, and I'll concentrate really on how point-to-point communication works here. Oops, sorry. I just want to double check. Yes, fine. Point-to-point communications. So we've talked about the small messages. Point-to-point communications typically incur startup cost, which is the latency, and we have a bandwidth. So the time to send data between processors is the latency plus the number of bytes divided by the bandwidth. And we saw this is a few microseconds. This is in the gigabytes per second. It's faster to send one large message versus many small ones, and so a standard other trick is to do one OR reduce of 2 doubles versus 2 OR reduces of 1 double. So that is, often you'll have a number of scalar quantities to add up. You might have the I don't have an example here, but you might have, you know, the pressure, if you're doing a climate modeling code, the pressure, the rainfall, and the temperature, for example. You want to average all of them. Don't do 3 all reduces of 1 double, do 1 all reduce of 3 doubles. It will take exactly the same amount of time, okay? So for example, you know, people sometimes get confused by this. I say, if you want to buy 3 pints of milk from the supermarket, is it quicker to go to the supermarket once and buy 3 pints of milk, or go to the supermarket 3 times and buy 1 pint of milk each time? It's obvious that the time of actually buying 3 pints of milk versus 1 is negligible. It's all in the getting there and back. It's all in the coordination. So you should. That is something which can work. You might say, well, actually, I can't do a single or reduce because I have mixed types. I have integers and doubles. Well, you can, if you're clever, you can use derived data types. So you can do a single or reduce to add up a mixture of double precision and integer data, or you can just convert the integers to doubles as well. But that is a standard optimization trick. I mentioned before, clearly you should send a small number of large messages when you're doing point to point, but that translates to collectives as well. So the collective operations all reduce have a count, and that is in many programs 1, but it can be more than 1. So don't do 3 all reduces of count equals 1, do 1 all reduce of count equals 3. So that is a useful technique. But so communications patterns here, this editing through the OO design, it's quite difficult to work out the timing of your communications, because I said you may have a mental model of how your algorithm works, but at runtime things may be a bit different. There are a number of standard patterns which can be the cause of poor performance. You can identify them by eye or by experimentation, but they could be detected automatically. I'll come back to this. Scholastica is a tool produced, well, by a bunch of people, but I know the people from the Unix Supercomputing Center, and it's a free performance analysis tool, but it not only measures the performance profile of your code, but also tries to, and doesn't just tell you this code spent a lot of time in this routine. It does try and recognize patterns, and it will try and say, this looks like a problem with this particular pattern. And so I'll cover the patterns, but tools like Scholastica make an attempt to actually correlate poor performance with known communications patterns. I'll become more obvious when I show you some examples. So late sender, okay? Classic one, you issue a receive, okay? But the send, so time is going from left to right here. This is when it's issued, this is when it's completed. You issue a receive. If a blocking receive is posted before the matching send, the receiving task must wait until the data is sent. That's kind of obvious, but that is, you know, that's often a symptom of load imbalance. Okay, late send is often an emphasis, whereas this process is running ahead of itself. It gets to the receive quickly before this guy gets there. So that's called a late sender. There's a large gap. This receive can only complete when the send happens, and there's a large amount of time spent in the receive. Out of order receives, late sender could be the result of having your receives in the wrong order. So you're expecting 2 messages from this guy and this guy. You issue a receive to this guy first, okay, and a receive to this guy second. You should have put them the other way around, okay. So naively you say, well, that's obvious, okay. I should issue the receive from this guy before the receive from that guy, so it will be quicker. Of course, in practice, this was not predictable. In practice, the fact that this send happened before that send was just random, and the next iteration, it could happen the other way around. So although this is a genuine problem, which we should try and address, it's rare that you can say, oh, clearly I should receive from rank 2 after rank 1. So I should receive from rank 1 first, then rank 2, not rank 2 first, then rank 1. Rarely can you do that, but we'll see other techniques to do this. But yes, out of order receives can be the result of having, late senders can be the result of having blocking receives in the wrong order. I think I heard a question. Why is the top part of that? So what we're saying here is that, okay, so the sends are the same, but here, let's call this 0, 1, 2. Okay, they should numbers. Here you've got a receive from 1 sorry, that. Here you said, I want to receive a message from rank 2, then I want to receive a message from rank 1, okay? But so you issued the receives to be from rank 2 first, then rank 1. But when you issued the receive from rank, sorry, you issued the receive here from rank 2, okay? It wasn't ready, but the rank 1 comes in first. So you shouldn't be receiving from rank 2, then rank 1. You should be receiving from rank 1, then rank 2, because that's the order that the sends are posted. Does that make sense? Maybe ran over that too quickly. Okay. Yeah. Okay. So so it's basically saying you want to receive the messages in the order they were sent. Here, rank 1 sends before rank 2, but you're receiving from rank 2 before rank 1. But as I said, so that seems like an obvious thing, but in practice, you don't know what that order is going to be. So you can't just say, okay, but there are other techniques for solving that. Late receiver, if send is synchronous, data cannot be sent until the receive is posted. Now, that may be an explicit synchronous send, but also it could be because you're doing an MPI, a standard send with a very large, well, largish message, which will be implemented with the rendezvous protocol, will be implemented synchronously. So again, late receivers, I issue a send here, but the receiver is slow, so I sit in the send. Okay, so this is a late receiver. Okay, so the sending task is delayed. So all of these are, you know, basically your sends and receives are issued at different times. So this is slightly subtle, but it is worth mentioning because the final pattern is quite hard to get your head around, but if you don't have a model. So I've sort of mentioned this, you probably think of MPI as running continuously. So when you issue asynchronous or non-blocking comms, you think they happen in the background. So your model is that while your process is calculating, the MPI is doing all the communications. This is actually not generally true. So the MPI library is single-threaded by default. Communication can only be processed when your program calls an MPI function. So I kind of mentioned before, what happens to MPI treats library causes manual interrupts. Whenever you call an MPI, whenever you enter the MPI library, MPI goes, great, now I can go and tidy up all the stuff that needs to be done, do all my housekeeping before I actually do what David wants me to do. And so MPI, this is called progression. Whenever you call an MPI routine, the first thing MPI does is it tries to progress communications by matching all the outstanding sends and receives. So if you issue a non-blocking send, okay, if there's an existing receive, it will be it may be sent. If it's not, it's parked. But your model is that it's continuously progressing in the background. It cannot be delivered until you make another MPI call. Now, the obvious thing is it's an explicit MPI call. Sorry, so the diagram makes this easier. So basically, okay, the sender issues a non-blocking send, says, please send this data to this guy. At that point, this receiver has not been posted, so this has to be parked. So this process just remembers, I've got an outstanding message to this guy. Then this guy issues the receive, but there's no way that this guy can in this, we're not in the MPI library here, so this non-blocking send cannot be progressed. Sometime later, you call it a function, an MPI receive on this, which is unrelated to the communication. However, you call an MPI routine. The first thing the MPI routine does is, is there anything I need to do? Oh, I've issued, there's a receive outstanding from this guy. I can then do the send. So calling an unrelated MPI routine causes this routine to be processed. So the data transfer happens here, although that receive has nothing to do with that send. The only thing that they are related is they both enter the MPI library. So, so there's a, okay, so there's a question. I'll just, okay, so this is, so I've seen this, so this, apologies, I've jumped. This late progress is a weird one. but it's saying that, again, my previous statement was, if possible, post your receives early because they're already in place. But if you do a non-blocking operation and there is no matching receive, that non-blocking operation is parked and may not be actually kick-started again until the sender re-enters the MPI library, even if the call you're making the MPI library is unrelated to the one that you did with the send. Now, I've seen there's a question about non-blocking communications here. Yes, so Ricky said MPI is running concurrently. Yes, concurrently is the right, I guess, is the right thing rather than in parallel. Yeah. Now, Mark says a code line works every double complement is double undermined. Didn't seem to improve. That's interesting. Yes, all I can think is that if you wrote a synthetic benchmark for that mark, you would probably see the effect. The problem is, yes, that synthetic benchmarks measure, again, yes, again, if the total time spent in this was small, then you wouldn't have noticed the difference. You did the right thing there, though, you know, sending two messages for the two parts of a complex number is not a good thing to do. So you did the right thing. But again, if there was any load imbalance, that would have completely swamped the time. The problem is, Ian, I don't know if I quite answered. It doesn't mean you need to trade off forward with asynchronous. Some people have suggested you ought to be able to just call a progress routine. You ought to be able to say, advance the MPI library. I think that the what I'll say is that these all show single sends and receives. What I'll go on to, it's a more general statement. Hopefully, I'll answer your question. What I think the best way is to do communicate. So I'll maybe run ahead of it for the moment. So both late sends and late receive may be avoidable, more careful ordering of computation and communication, but often they're really due to random noise. So not all tasks take the same time to do the same computation. Not all messages take the same length, take the same time to arrive. So you know, you can even see this. Yeah. So you know, if there's network congestion and you don't know about it in advance, obviously, then your process will get out of sync. So what the general approach is, if you have lots of communications to do everything non-blocking. Okay, issue all the sends and receives as early as you can, and then do a wait all. Because by doing a wait all, you're telling MPI, look, I've got lots and lots of communications going at once. You sort it out. You process them as and when they arrive. The problem about using waits, for example, is you're prescribing an order. So your aim here is not to prescribe an order. So what you do is you issue all the sends and the receives, and maybe in 2D halo swapping that would be, in a 3D halo swapping that would be 12. That's 6 sends and 6 receives. You have 12 communications going at once, and you don't assume what order they'll complete. You tell MPI wait on all of them to finish. And by doing that, MPI can basically deal with them as and when they arrive. And that's the kind of general advice that I would give. And hopefully we'll see that actually has a beneficial effect when we run the benchmark. So yes, so Stephen's question, aren't these don't send it? Yes. So I said the way to ungum them is people did suggest an MPI progress command, which says do nothing but progress the I mean, there are attempts on ARCHER2. You can actually run MPI in a mode where there is a thread which basically loops and kicks the MPI stack every now and again, which to ungum them. But unfortunately, that requires you to use a thread safe. We'll talk about this tomorrow. A thread safe version of MPI, which has a huge overhead in itself. So it's really a design problem there. I don't think MPI would be designed like this today. MPI today will be designed to take advantage of the fact that you have lots of processors, processors, all of which can run lots of threads. So I don't think that this is the way MPI will be designed today. But MPI was designed back over 30 years ago specifically to be able to run on processes that had no threading, which could only a process could only run one thread at one time. So there was no concept of interrupts or something. It had to always have to be done manually. So wait any is useful if you have something to do. So if you just want the communications to finish, then you would just use wait all. If you were if you had to do so imagine you were expecting data to come into a buffer, but after arrival that then needs to be copied somewhere else. Okay, you could loop round a wait any, and as every message came in, you could say, right, that one's finished. I'll then copy that to where it needs to go, and then move on to the next one. So wait any would allow you to deal with the messages in the order they came in, which would be a good thing to do. Wait all says wait for them all to finish, which is fine if you're just expecting the data to arrive. There's nothing to do with it. You just do a wait all. If there is some actual processing you need to do on that incoming data, like copy it to its final destination or unpack it or something, then yes, wait any would be, you would loop over wait any, potentially loop over wait any many times. Yeah. Again, sometimes though, the more clever the loop and sometimes people put a lot of effort into in principle writing very efficient algorithms where they deal with them. Sometimes it's just simpler to wait for them to come and deal with it all at once. Sometimes they simplify the logic. But yes, that is that is wait all is just for halo swapping where the data is just arriving. If there's processing to be done, then wait any is a useful way of doing it. Okay, they're very interesting questions. All non-blocking comms. Yeah. So this is sort of normal halo swapping. We've got a situation where we have an array with some boundary data. We want to halo swap it. Okay. And I've just got the example here where I'm doing some stencil up, down, left, right. But we've got 4 halos here, basically. That's a standard halo swapping algorithm with a 2D stencil. Don't impose unnecessary ordering of messages, okay? You could do loop over sources, up, down, left, right, receive the value from a particular source, end the loop, okay? You could try and use MPI any source. You could loop over the sources, receive the value from any source and end the loop. However, it's actually better. Wildcarding has its overheads. So I think you just won't want to do this. So definitely you don't want to do this. You don't want to say, I want to receive up, receive down, receive left, receive right. You could do 4 receives where you receive from MPI any source. That doesn't feel right. The best thing to do is non-blocking here. Okay, issue a separate non-blocking receive for each source, then issue a wait all. So do not impose unnecessary ordering of messages. Loop over directions, send up, receive down, send down, receive up. Okay, you don't want to do that. You want to loop over directions. You want to do an I send up and I receive down, and I send down and I receive up, and then wait on all the requests. So you issue all the sends and receives up, down, left, right, forward, backward. And I said that's 12 communications in 3 dimensions, and then wait on all of them to finish. And there's even more. You can be more clever and overlap communication with the core calculation if you want to be clever. I think I heard a question coming in. So yes, so this is illustrated by my benchmark. I don't like send receive, okay? Because send receive is prescribing a pairwise synchronization. And so you'll see in the halo swapping benchmark that send receive is not a good thing to do. Sorry, not an optimal thing to do. Apologies. You know, what you can do now, if you want, is you can say, basically, you can send off the boundary data, do all the communications on the interior region, on the interior region here, okay? So I update the interior. Now I wait for the completion of non-blocking send receive and complete the calculation of the 4 edges. That's another technique that people do. It may or may not help you, but it's something which people do. And a final thing, sorry, I've got something funny with my mouse here. Some people you can try and so in this situation we swap a halo of depth 1, we swap the near, allows us to do one iteration before we have to swap the halos again. You can say, well, let's trade off latency and bandwidth and swap a deep halo. We'll swap a halo of depth 2. That allows us to do 2 iterations before we do an next communication. So you do 2 iterations, and then you communicate twice the data every other iteration. That, in principle, you might think is a good idea. The problem is, in practice, it has its downside. That if I don't want to go on about this too much, but if you think about it, it implies it implies diagonal communications. So with this standard up, down, left, right stencil, we only have to communicate with our 4 neighbors. If I want to swap halos of depth 2, I need to communicate that data there, and that is a diagonal communication. So you have to send that data up, that data right, and that data diagonally, unfortunately. And so, although deep halos sound like a good idea in principle, that you do, you only communicate every 2 iterations, and in practice, they do have their disadvantages. Yeah, that was just you do 2 calculations for each communication and then halo swap again. I'm not really because it implies diagonal communications. I've mentioned persistent communications actually. This is just a repetition that rather than doing I receive, I send, and await all, you can set them up once and do it. But again, in practice, persistent communications have almost no benefit. In principle, MPI can skip the error checking. So what it can do is here, in principle, MPI has to do an error check on all the variables for every call. Here, it has to only do the error checking at the initialization, and it says everything's okay, and then it knows that they're all. But in practice, that's of negligible benefit. So I'm not going to talk about neighborhood collectives because that was something that I was going to. I'm not going to talk about those. I'm running slightly late, but the collective communications that have all the same issues, in principle, the same patterns, patterns for poor performance as point-to-point do. So, for example, if you have a late broadcaster, yes. So there is actually. So I'm surprised. Sorry, I have put this talk together from a couple of other talks. There should have been a slide after that that says exactly as you said. Who's Stephen? Yes. So you're absolutely right. Can you see my? You can see my camera. What you're saying is that if I do the horizontal communications first, then when I do the vertical ones, I can carry that data. Yeah. So you're correct. However, that implies more synchronization because you basically then have to synchronize for each dimension. So it's probably better than the explicit diagonals, but it does have its downside because you basically have to complete. You then have to have an ordering. You have to complete the horizontal swaps before the vertical ones, before the ones in the 3rd dimension. So you're absolutely right. That is what you can do that, but you then lose the fact you're then imposing more synchronization because you have to order the halo swaps. One has to complete before the next one. Each dimension has to complete in turn before the next one can take over. So it's just nasty. It sounds like a really good idea, but it just never really seems to pan out. Does that make sense? Does that make sense to you? I think that's what you're saying there. Yeah, so again, it has its downside. It might work for you. What I would say is the biggest mistake people make, if they write a program with all these bells and whistles and never have the default implementation, if you have a groovy version of the algorithm, make sure your code also has the simple one, because sometimes the simple one can be faster, because all the extra logic and messing around and branching and of the complicated algorithm may not be worth it. So it's fun to do, but you really should, at the end of the day, time it. That's the biggest mistake people make, is they only have the complicated algorithm. Keep the simple one in, so you can run them all and see which one is actually faster in practice, because it will depend on the target architecture, but they all have their downsides. So late broadcaster is just, you know, if the person who has the data comes in, then you can see this often happens because rank 0 might be reading in a file, then broadcasting, and all the other guys go on to broadcast first. But it's the same for any collective. Early reduce, yeah. If one person calls reduce and not everyone is ready, then you're going to have a lot of time spent. And all-to-all, again, in algorithms which have global transpositions, like Fourier transforms, where you're doing effectively transposing the data array to make different dimensions local at each phase, you have an all-to-all, and that again, there needs to be synchronized. There needs to be that will show up load imbalance. All I'm really saying here is that all of these, all forms of collective communication are likely to show up as load imbalance. So yeah, so oops, so well, I'll just slightly rejig the title, but the collectives are hopefully well optimized. It's rarely useful to implement themselves. They are expensive and force synchronization, so you should use them as apologies. Use them as they use as far as possible. But in many, yeah, we've talked about this. Now, non-blocking collectives are out in MPI 3, okay? So you can actually call a non-blocking collective. In practice, I have never found them of any use. I mean, we can discuss this offline, but there are algorithmic reasons, because if you look at things like iterative algorithms like conjugate gradient, you always need the result of the dot product. Immediately you compute it. Alpha equals x dot x, and then the scalar alpha is used in the very next line. So algorithmically, I have never seen them do that much use, and in practice, they don't seem to be implemented. That I struggle to see, other than a very few niche areas, I struggle to see situations where non-blocking collectives actually help in practice. They sound like a great idea, but I'm not convinced they are. General advice, try to avoid imposing any non-essential message ordering, because the actual message ordering can change each time you run it. So my general advice is to try to allow MPI to deal with the messages as they happen. Issue all sends and receives as non-blocking. Also issue the receives as early as possible. Often, because remember, as I said, if the receives are in place, the sends will complete quickly. And often you can pre-post the receives. You might be tempted to post the receive at the beginning of your current iteration. Sometimes you can pre-post them at the end of your last iteration. It kind of blows your mind, but sometimes you can actually pull the receives quite high up. Set up as persistent comms or use neighborhood collectors. Avoid unassigned collector caused each by aggregation. And do you really need any of those barriers? That's always my big question. So we've talked about these. Lack of parallelism and load imbalance are very difficult to deal with because they're algorithmic. Synchronization is you can improve this by not having the process waiting for each other, and an inefficient pattern of communication you can address. I mean, it is quite tough. I think it's useful to have these models, and these terminology like late sender, late receiver are useful when talking to other people. Have a common framework for talking about these things. But if there's one thing I would say, maybe said it too many times, if possible, just don't impose an ordering. issue all your communications as non-blocking calls and have a single wait all to and then allows MPI to deal with them as and when they come in. And the exercise we'll do after the break is to run the halo swapping benchmark, and we will see which of these is fastest in practice. So there've been lots of interesting questions there. I think that I'm not going to have a chance, as I sort of rejig the timetable because of ordering things as to how people express their preference. I'm not going to have time to do the my brain is going, the optimized, the trendy use of derived data types for advanced collectives. The lecture is still there. I think the best thing to do is maybe take a slight, my voice is going a bit, so if we take a 20-minute break and come back and then concentrate at the end on doing the halo swapping benchmark. And I might just explain the crux of the issue with the derived data types vis-a-vis collectives, but I don't think I'll have time to go through the whole lecture. So as I said, my voice is slightly giving out, but what I will do is the next exercise is the which we'll do when I come back in about 20 minutes time, is the halo swapping one, which is in the Git, read it 15-20. I was just about to, but I would be quite interested if someone could redo, and I've not done this, if someone was keen, they could redo the point-to-point ping pong using the UCX protocol, which it's just a matter of swapping some modules. So you'll see there, I've got a link in the instructions. They're actually part of the halo swapping benchmark, but they apply equally to the ping pong. If you could, maybe somebody could run intra-node ping pong using UCX, and you don't need to recompile, it's just a module swap at runtime. That would be very interesting. It might try and elucidate what the issues are. Okay, thanks. So see you in 20 minutes. I've got to get some more water.